we start discussing on the three-phase AC circuits. And the first thing we did was the advantages of polyphase system, why this three-wire system is there. Okay, and we briefly introduced about that how the three-phase EMF is generated. So we told that in the in the three-phase system is basically three single-phase systems are there inside the generator, which are 120-degree shifted from each other. The windings are shifted from each other, and typically these windings are known as RYB system. If you see the inside of a generator, the windings are basically have three colors: red, yellow, and blue, and that is how it is known as the RYB system. And the EMF is generated when there is a moving magnetic field, and inside basically there is a magnetic field. A magnet is created which is rotating. Okay, so the windings are stationary, but the magnetic field is rotating. Okay, so it can be the diagram that is shown here basically shows there are two poles, north and south. Okay, so this is two poles. So obviously there cannot be less than two poles. So the two poles are there, and it is rotating. And we saw what is the synchronous speed expression. Now there was some many interesting questions, and since it is a polyphase system, and if there are more than two poles, some of the students asked the question. So I found out some diagrams. Okay, can you see this? The diagrams I found out.
Yes, sir.
Yeah.
Yes,
So
sir.
yes, sir. So the leftmost diagram, it basically shows a cylindrical rotor. Cylindrical rotor means you see that it has two poles. Okay, the north and south, but the rotor is actually cylindrical. Though for explaining in the previous figure, in the previous slide, it was just two poles. It would look like a bar magnet. Okay, but in actual construction inside the generator, it is actually cylindrical in shape, and this is how the windings are. So if you make the winding, okay, for explanation sake, we just told a bar magnet north south, but that magnetism is actually generated by a coil. Okay, by passing current through a coil, and you know that when a current passes through the coil, in what direction the field lines will be and how the polarities are created. So that is the uh, field is created inside the generator, which actually moves. So the left one diagram is basically showing a cylindrical rotor. The rotor is the shape of the rotor is in the form of a cylinder, and this basically shows the cross-sectional view of the generator. Okay. So between the stationary part and the moving part, which is the rotor, so between the stator and the rotor, obviously there is an air gap. They should not touch each other because these are rotating at high speed. Okay, at 3000 RPM. If you go to aircraft generator, they are running at 10,000 RPM. There are high speed machines are there, and so they should not touch each other. So there is a gap which is known as the air gap. So this is how the field is created inside the rotor, the cylindrical rotor. Similarly, as I told, there are more than two poles are possible, four poles, six poles, and all. So if this right figure shows if there are four poles, it will look like this: north, south, north, south. Okay, and the polarity is created by the windings, by the coils, and by the direction of the current flow, the polarity is actually created. So it is the north pole, south pole, north pole, south pole. Uh, that is so. So this structure on the right side, it is not cylindrical in shape. Okay, it is basically it looks like a cross, look like a plus sign. Okay, so this rotor is not cylindrical, so it is called a salient pole rotor, as if the poles are just projected out. Okay, and the rotor is moving. So one disadvantage with this
Actually,
salient,
sir.
yeah.
So I did not got that. So in second diagram, sir.
Hmm.
So North Pole and North Pole are on opposite sides, sir. That's same bar.
No, that polarity is basically created by the windings. You see the north pole, there is a coil. Okay, so the direction in which the current will flow will create the north polarity here. Similarly,
Okay.
for the south pole also there is so this is basically a structure on which these iron pieces are mounted, and then actually the coil and then the current through the coil decides the polarity. Okay.
Okay, sir. Okay, sir. Got it, sir.
So that means that the polarity is generated by the coils itself.
Yes, yes. The polarity, because it is the current has to flow, and that is basically a DC current. Because if you have a permanent magnet, okay, it may demagnetize with time, with age. Okay, so then
So that means That means we are first converting from mechanical to electrical, and sorry, the electrical to mechanical, and then again mechanical to electrical in these generators.
Now, why mechanical to what? I couldn't understand.
So that means when since the coil is generating the polarity, then no, sir, I actually confused. Okay.
Okay, because the coil is there, that is another separate power supply, and that is basically DC power supply.
Sir,
Okay,
sir,
yes.
sir, yesterday you had told that for more than two poles we take more than one magnet.
That was just for telling, but in actual practice, this is implemented this way. Okay, this is North Pole, South Pole, North Pole, South Pole, and in below diagram you see there are even 8 poles, and you see there are windings. This is called the field winding because the polarity is created by a separate supply. Now,
Sir, on the salient pole rotor diagram, why it is written that north and north are on opposite sides and south S and S, I mean N and SS. Why is it so?
no, no, it is not a single pole. The polarity is created by the windings. There is a coil here. If you just see below the north, there are two wires. It is basically a coil, and the direction of the current through that coil will generate the polarity. So we
Okay,
will
sir.
have
I got
alternate
that.
north-south condition.
Okay, sir. Okay.
Okay, now the rotor is actually moving at a high speed. Okay, now that the disadvantage of the salient pole structure is, whenever there is a speed, what will happen? What will happen? What type of force will be generated?
So centrifugal.
Centrifugal force, and these poles will try to move
Centrifugal.
out. Okay, if
Yes,
the
sir.
pole, so they have to be very mechanically fastened, and so for the salient pole structure, you cannot have the rotor rotating at high speed. So they are actually used in generators which are rotating at low speed. Okay, there are some low speed generators, just like the hydel turbine. Okay, water is falling, and the falling water is used to rotate a turbine, and that is actually slowly moving. Okay, so that cannot move as fast as a steam driven turbine. Okay, so for the hydel generating stations, the generating stations using hydel power, they use the generator which is salient pole in structure. Okay, that is low speed. You cannot use the salient pole in the steam turbine because it is at high speed, or even in the gas turbine in the aircraft. Okay, aircraft turbine is rotating at 10,000 rpm. Okay, the steam power plant's turbine rotates at 3,000 rpm. So at that high speed, if you keep a salient pole structure, the poles will need a huge mechanical strength because they are projected out and they can fly out by the centrifugal motion. So the salient pole structures are basically used in generators that are slowly moving. So that is the purpose of these two structures. So the purpose of showing this figure is this is how multiple poles are generated.
Sir, I have
So,
one question.
mm,
Sir, here in this like salient pole rotor, we are
mm,
using like two opposite S, like we are adjusting the current direction so that the like the parts of horizontal, if we say the bar, both
mm,
are S. So inside
mm,
there will be north poles, right, facing each other. So they'll repel each other,
mm.
and hence the probability of flying out will increase, chances of flying out. So like why don't we
No,
do this?
acha. Yeah.
No, no. See, the thing is, there is always the probability of flying out any time because they have to be mechanically fastened. Okay, they are
So, but
they
if
are
the
tight.
magnets also attract each other, it will be
Mm.
easier. Like it can go up to higher speeds then.
No, but you see, if it is north, this north will be the adjacent ones are basically south. The adjacent ones are basically south. So there is an attraction also.
Acha, yes.
Sir, I
Okay.
have another question here.
Mm,
Sir,
mm,
we have seen previously that there are three coils R, G, and B, where at a time one is kept such that the flux passing through one of the coil becomes zero. But if we keep a salient pole or a cylindrical rotor,
mm.
I mean, in a salient pole rotor, there would be a single time when the flux passing through one of the coils will be zero. I mean, that case will never come.
No, it is
But
not flux. It is. It will. It will. It will momentarily come for a fraction of a second. It is moving very fast. Okay, so this you can calculate if it is 4 pole, what will be the speed?
Sir, we have to calculate like that from formula from
Uh,
120 into
120
P
120 f
divided
by
by
p.
4. Yes,
120
sir.
f by p. So what is the speed?
So
1500.
30 into 50, 1500, sir.
1500
1500.
1500 revolutions per minute.
Yes, sir.
Okay, so per minute 1500. So in per second, you imagine how much. So at what speed it is going. Okay, so eventually it is the sinusoidal structure that is generated.
Okay, sir.
Okay, so for the more details about the cylindrical salient pole and all those things, there are advanced courses on electrical machines taught in second year, third year. Then these are taught, there are elaborate courses on machine design, how to design these machines. So those things we cannot teach in this course, but just to show you that there are multiple poles there, it basically looks like this. So, and that is basically mounted in the rotor. And the
Sir, can we have odd number of poles?
huh?
Can we have odd number of poles?
No, there is no odd number of poles. You have to maintain certain balance.
Sir, what is that about North Pole and
Hmm?
salient pole rotor?
Hmm.
What is those 5 dots type thing in
That is
North above North
that,
Pole?
that is the stator slots. You see it written stator slots. That is the one that is static. The rotor is moving, so the outer one is static. Then inside is the rotor moving. So that is basically the conductors in the stator, which is basically that RYB. They are spread out throughout the stator. This way, they are spread out throughout the stator. Okay, is it okay?
Yes.
So that means a small part of the generated electricity goes into determining the polarity of these magnet heads.
Yes. Some amount of energy is required to generate this magnetism also.
Yes,
Okay,
sir. Yes.
but
That
that is
means
very.
to start the motor at the initial point, we have to use a capacitor as starter or something.
Not capacitor. It is basically it is a DC source is present there. Okay,
Okay, sir. Okay, sir.
this DC source is present there to start this, because that is the thing. Because just before starting generating the EMF, you need the field inside.
Yes, sir.
Okay, okay, so that is a separate source. So this slide I added because some of the queries regarding this inside polarity I searched out and added. So let us begin from okay, where the slide is visible.
Yes, sir.
Yeah. So then we discussed all these things. This I am not going to discuss. We have done a lot on this. So we this also we have done RBY, RYB, and three-phase four-wire, three-phase three-wire, and I think we are doing this. Y-connected generator. Did we complete this?
Yes, sir. Yes, sir.
Yes,
Hmm.
Yes, sir.
So you see Y-connected generator because the three phases is yeah.
sir, I have a doubt in previous slide.
Hmm. Which one?
Sir, as that rotor will rotate, then the wires which are responsible for generating magnetism will also rotate with that. Then they will mess up.
They will.
They will mashed up, na sir. The wires will break.
No, there are mechanical arrangements so that they don't break. They are solidly they are fastened so that they don't break. There is an elaborate mechanical arrangement. It is more of an mechanical type of work. Okay, they don't break. Okay, there are mechanical special arrangements too, so that it is very robust. And if you actually work in a power plant, if you actually work inside a generator, you can see those things. So I am telling this from my own practical experience. I have actually worked in the power generating station of different types, and in fact, I was actually working inside the generators only. So I know how the construction inside is. So basically, it is a mechanic. It is the the mechanical design which actually matters. Okay. So we are doing this three-phase Y-connected generator, and as I told that as soon as you tell Y-connected, we have to tell the phase sequence. And as soon as you can tell the phase sequence, you can write down the equations. So this is an ABC phase sequence. So A is followed by B, and then it is followed by C, and then we know how the phasor diagram is going to look like. So VAN is along the reference, which is VM angle theta. The magnitude is VM and at an angle theta. At an angle 0 degree. Then the VB is at an angle minus 120 degree, and VC is at an angle minus 240, which is equivalent to plus 120 degree. Okay, so this is how the three phasors of the three phases will look like. And we also find out, if you have tried to find out the voltage of A with respect to B. Okay, so these voltages A and B and C are with respect to the neutral N. Now, if I want to find out voltage A with respect to B, it is VAB is equal to VAN plus VNB, and VNB is basically equal to minus VBN. Okay, so VAN plus of minus VBN. So how do we get minus VN? We reverse VBN. We do the reversal of the VBN, and then you add to VAN. So that then you all are experts in doing that addition. Okay, it is just like the addition of forces. So you complete the parallelogram, and then that basically gives you the VAB, whose magnitude is which is at an angle of theta with respect to the reference, and its magnitude is also root 3 times the individual phase voltages, magnitude of the individual phase voltage. So VAB is equal to root 3 VM, and it is located at an angle 3 theta. So it is advanced with respect to the reference or with respect to even the A phase voltage. Okay, so that is VAB. Similarly, you can find out VBC, which is VBN plus VNC, when NC is plus or minus of VCN. And so to do that, you have to basically reverse the VCN and then add to VBN. And it will be somewhere here. And again, VBC is root 3 V times VM, and at an angle of minus 90 degree. Similarly, VCA equal to VCN plus VNA, and which is equal to VCN plus of minus VAN. And so to do this, you have to basically keep VCN and reverse VAN, and then do the addition, which will eventually look like this. So VCA. So these VAB, VBC, and VCA are basically in the, these are called the line-to-line voltages. A, B, and C are the line voltages. So these are line-to-line voltages from A to B or B to C or C to A. And they are basically root 3 times greater in magnitude than the magnitude of the phase voltages, because it is for this star connected generator. For this Y connected generator, the line-to-line voltage is root 3 times in magnitude compared to the magnitude of the phase voltages, the individual phase voltages A, B, and C. And they have their own angles, and how to generate their angles we have just now shown. Okay, so these things you have to remember. So that for a Y connected generator, the magnitude of the line voltage is root 3 times the magnitude of the phase voltage, and you should be able to also construct the angles, how the angles are generated.
Hello, sir.
Yeah.
Sir, can we increase the voltage by connecting VCA and VAB? And there are three pairs like VAB, VBC, VCA. So, sir, can we connect VCA and VAB to get 3 times of voltage of VAB?
That you check, because this is all vector addition. Whether by doing this vector addition it increases or not, you have to find out.
So I don't think it will increase. It will be of the same magnitude. They are at 120 degrees to each other.
It will be
So
select VCA then. Sorry, VBC.
Okay, sir.
Okay, so if it has to be phasor addition. So after adding the phasors, if the origin and the tip is at the origin again, so then it will become 0. Okay, so you have to see what you get actually by drawing the phasors. Okay. So this is the Y connected generator, and obviously Y connected generator when the phase sequence is ABC. Now suppose if I change the phase sequence to ACB, okay, So find the line voltages for the phase sequence ACB. So as soon as I tell you ACB, what you can do? You can write down the voltage equations. ACB. So A will be VM angle 0. Then what will come? VC will come. VC will be
Yes, sir.
VM angle minus 120 degrees. So there is the VC. Because I have given you the phase sequence ACB. Then that will be following the C will be the B phase, which is at an angle minus 240 degree or equivalently to 120 degree positive. So if the phase sequence is ACB, this will be the phasor diagram. And now if you are asked to find out what is the VAB, VBC, you can again do. Okay. So to do VAB, what you have to do? It is VAN plus V plus or minus of VBN. So you have to basically reverse VBN and then add with VAN. So your VAB is here. What is the angle?
Minus 30 degree. Minus 30.
Minus 30 degree.
Minus
And
30.
and magnitude?
Root
Magnitude?
3.
So it will be
3 times the maximum.
so the magnitude is root 3 times VM at an angle minus 30 degree.
Yes, sir.
So you see the VAB has changed because I have changed the phase sequence. Okay, the earlier VAB is different from this VAB because here the phase sequence is different. Phase sequence. So VAB is root 3 times VM in magnitude, but it at an angle of minus 30 degree. Similarly, you can find out VBC, which is V, and VC is reversed, so you will get VC here, and VBC here, and which is at an angle of 90 degree.
90 degrees, sir.
Okay, similarly, you can find out VBC, VCA. So VCA will be VC and VA reversed. The addition of VA reversed will be here and completing the
210.
parallelogram. So what is the angle?
Minus 150.
210.
Minus
150.
Minus
150 or
Minus
you
150.
can also find out the equivalent positive angle, whatever it is.
Plus 210, sir.
Yeah, so this is how you get the angles. Okay, all of you get ready with calculator. We'll do a lot of numericals today on 3 phase. So VCA is so you see the phasor diagram is important because I have changed the phase sequence. So as soon as I change the phase sequence, you should be able to write down the individual phase voltages and then find out the line voltages. Okay, so the line voltages, so you have learned how to find out the line voltages if the phase sequence is changed. Okay. Any question on this?
No, sir.
No, sir.
So what is the use of doing changing the sequence? What is the use of any advantage of changing the sequence?
There may be in some applications where the phase sequence has to be changed. Okay.
Sir.
There may be there will be some applications, but these are not to be discussed here in this curriculum. Where suddenly a machine is operating and the phase sequence is changed for some other purpose. Actually, mostly it can be even used for braking. Okay, like suppose there is a traction motor pulling a railway engine which is connected to a huge goods train. Okay, so the motor is basically operated in a particular phase sequence, and there is actually another way of braking the engine, just by changing the phase sequence. So that will actually happen. Require is just changing the phase sequence, and it does not need the mechanical brakes. Okay, there is no mechanical braking, so that is how also the braking is done. So that is one application where changing of phase sequence will be there, but those are things will be taught in your second year, maybe third year of the electrical engineering curriculum. Okay.
Okay, sir.
But here, if you are given a phase sequence, you should write down the correct phase equations, and then draw the line, find out the line values, and and since everything is phasor, you have to be very much correct in the magnitude as well as the angles. We'll do numericals on this actually. Now, Suppose there are three impedances, Z1, Z2, Z3. You know what is the meaning of impedance, and they are connected together. So what type of connection is this?
Y
Parallel.
connection. Y connection.
Parallel.
So Y
Huh?
connection.
The Y connection.
Oh, the
Y
Y
connection.
Y connection.
Y connection.
Y connect.
I have not connected the left end. So what is the why is there that some answers are there for parallel? So
Yes,
this
sir.
is basically the Y connection.
Yes,
So
sir.
three impedances are there, and if their one ends are kept fixed and kept made common, okay, and the other ends are coming out, it is basically results in the Y connection or the star connection. Okay, we already did earlier the star to delta conversion. This is basically star connection, but only the change is that only impedances are involved. Similarly, so this is basically called the Y connection or the star connection. Now, if you have three impedances Z1, Z2, Z3, and they are connected this way. Okay, the left end of Z1 is connected to the right end of Z2. The left end of Z2 is connected to the right end of Z3. And again, the left end of Z3 is connected to the right end of Z1. Okay.
So delta connection.
So you basically end up
Delta
getting this type of connection. Z1, Z2, Z3. So these are all impedances. Okay, so all these Z's are basically having a real part and an imaginary part. So these are impedances. Okay, these are basically the loads. There is no generator here. So this is the loads. If you take three impedances and connect in the star form, or you can even connect in the delta form. Okay. So the earlier thing that we were doing was the star connected generator. Okay, star connected generator, and we changed the phase sequence and did all those things. But right now we will also see that the load also has to be connected. Okay, there is no requirement of electrical engineering if there is no load. Okay, we all want to say run some fan or light some bulbs, light some lamps, or use the electrical energy for some purpose. Okay, so there is a requirement of load. So this is how the loads can be connected in the three-phase system, either in the star configuration or in the delta configuration. And load is basically an impedance. And we know what is the meaning of impedance. It is having a real part and an imaginary part. Now, the values of Z1, Z2, Z3, all of them can be unequal. If Z1 is not equal to Z2 is not equal to Z3, okay, or they may be exactly equal. Okay. The value of Z1 should be exactly equal to the value of Z2 or equal to the Z3. Hello. Yes. Can you call after 4 p.m.? I'm in a class. Okay, so the impedances may be unequal. Z1 not equal to Z2 not equal to Z3, or the impedances may be exactly equal. And exact equality means their real parts should match, and then their imaginary parts also should match. Okay, the reactance part should also match. Reactance part, if both of them, if all the reactances are inductive, they all of them are matching. If all the reactance part is capacitive, they are matching. So in that case, so both these possibilities are there. So if they are unequal, it is known as the unbalanced load. If your Z1 is not equal to Z2, not equal to Z3, it is known as the unbalanced load. And if they are all equal, they are equal in all respects. That is, the real parts are matching, and then the imaginary parts are matching. It is known as the balanced load. Okay, so as I have told you in several examples that suppose in your hostel there are three wings. Obviously, when you come back to your hostel, you will find that there are several wings in the hostels. Maybe 4 or 5 wings are also there. I'm just giving the example of 3 wings, and each wing will have different types of consumers. Okay, not all wing will be consuming the same electricity at the same time. So obviously, the impedances in the 3 branches, 3 wings will be different. But if it is possible, if it is somehow made possible artificially, to keep the impedances same, then it is known as the balanced load. Okay. Now, in your curriculum, in your first year electrical technology curriculum, we will not consider the unbalanced case. We will not consider unbalanced loading because that will actually result in a complicated three-phase circuits to be solved. Okay. So in the first year undergraduate electrical technology curriculum, we will only consider balanced loads where Z1 is equal to Z2 equal to Z3. And I have already explained what is the meaning of these equalities because all of them are complex numbers. And you all know better what is how they are have to be equal. Because all of these...
Sir, I have a question, sir. If Z1 is equal to Z2 and Z2 is not equal to Z3, then also it is unbalanced.
Yes, because there is one equality is not satisfied.
Okay, sir, got it.
Okay, all of the three together is the load, not just only two matching. Okay.
Sir? Sir, Z1, Z2 and Z3 are the impedance of the coil of the three-phase AC generator.
Where is the generator here? I have just kept three impedances.
Only impedance.
Have I kept any generator here? Is there any voltage thing I have shown here?
No, sir.
So this is just keeping impedances. The impedances can be connected in the star configuration. They can be connected in the delta configuration. And if all the impedances values are equal, whether it is in the star or in the delta, then it is known as the balanced load. Okay.
Sir, significance of balanced load?
Significance of balanced load means since all of them are equal, it will result in a we will see shortly, it will result in simplified calculation, simplified analysis. If there is unbalanced, all the power companies, they try to keep a balance between the loads. Otherwise, they cannot run the system. Okay, they somehow try to balance. If you go to your locality, there are several different types of consumers. There are domestic consumers. There may be some shops. There will be some diagnostic centers. There may be some hospital. There may be railway station. All of them are consuming electricity. So the electrical supply company, wherever you are, whether you are in Delhi, Bombay, Kolkata, or Kharagpur, whether it is a private company or it is a government company, they try to balance the loads because that way the generation will also be balanced. Because the generation is balanced, you cannot have unbalanced generation. Okay, so now if there are three-phase generators, okay, three-phase generator and load. So in general, so this is basically the generator. I already showed in my earlier thing that there is a generator, and from the generator basically three wires come out. One is known as the sorry, I have
Especially RYB.
Yes. It was taken from
RLC circuit.
No, not RLC circuit. It was, I made my slides from modifying my earlier module, picking up some of the elements from that, the lines and all these letters.
We always talk about RLC. And
so, can you see the slide?
Yes, sir.
Yeah, so basically these are some text boxes I picked up from the earlier module, so the RLC I forgot to change. So from a generator, basically three wires come out, and those are the three phases R, Y, and B, red, yellow, and blue. Okay, so a three-phase generator is also so where from will this go? You cannot just keep on generating, and it is going nowhere. Okay, you cannot just generate. Where should it go?
So to the load.
To the load. We all are consumers. We are consuming power. You are sitting in your...
Oh, sorry.
So you are sitting in your study room, or you're in your home. Some refrigerator is running, or some TV is running, or some other gadget is running. So all of them are receiving power. All of them are consuming power. So obviously there is somewhere some generator which is generating, and this power has to go to a load. Now in our case, since we have now started three phase, and three phase is the Three phase is the system that is where present in the general power system. So the load is a three phase. Okay, so the three phase generator feeds a three phase load. Now three phases means this there are three elements in the generator. There are basically three individual single phase sources. Okay, and they can be, if there are three elements, they can be configured in different location, different configuration, whether it can be in star or in a delta. Similarly, that three phase load, as we showed in the previous slide, are basically three impedances. So they also can be connected in the form of star or delta. So what actually happens is there can be several possible configurations, that the generator can be a Y connected generator and the load is also a Y connected load. The generator can be a delta connected generator and the load is a Y connected load. The generator can be delta connected, the load is also delta connected. Similarly, so if the generator is a Y connected and then there is the load is also delta connected. So there are different types of possibilities are there, and suppose there is a Y connected generator, we already saw that if there is a Y connection, there is also always a possibility of a fourth. There is always a possibility of a fourth terminal available, which is basically the neutral. So if there is a Y connection, there is a possibility of the fourth terminal available, which is the neutral. But if there is a delta connection, there is no possibility of the fourth conductor. Okay. So we'll see these different types of configurations. So this is clear? Yeah.
How is the circuit completed?
Huh?
How is the circuit closed?
Okay, so that is, I understand how is the circuit closed. That we will shortly see once I showed an actual circuit. It will be there in my next slide only. Here, this I just generated this block diagram to explain that there is a three-phase generator, then there is a three-phase load, and from the generator comes out are the three phases which feeds to the load. So I think actually the examples will explain how the circuit is completed. Does it answer your question?
Okay, sir.
We'll do now actually examples. I mean, we'll have to handle three phase.
Sir, in delta connection, what is the structure of generator? How the different phases can be obtained?
The different phases will be individually the different phases, like that Vm angle theta minus Vm angle minus 120 degree, and then they have to be you have to generate the phasors.
I mean that in three-phase one-wire connection, the magnet was being rotated in between all those three with the angle of 120 degree. But in this delta connection, how we can rotate a magnet between them, and how the phase difference?
See the magnet. So there are three coils inside the generator. Okay, and the magnet is rotated. So individually there are three EMFs generated. Okay, now how these coils are connected will generate the configuration, whether it is Y connected or delta connected. Okay, so we will, as somebody was asking, how is the circuit complete? I think it will be clear in the numericals. So that suppose you have a three-phase generator like this. Okay, and as I am telling you, in most of the times, the generators are actually star connected. Okay, I have actually worked in the power plants. So those of you who are from Kolkata, I actually worked in the power supply company that supplies power to Calcutta, the Calcutta Electric Supply Corporation, and in the generator division only. And I was actually working inside the commissioning of several generators. So the generators are actually star connected with this neutral available. Okay. So if this is the generation, so there's how these voltages can be represented in the phasor. Okay, so the voltages that VAN will be along the reference. Then it is, since I told ABC system. Okay, ABC system, so B will be 120 degree away from A, and then the C will be 120 degree again further away from B, and which is minus 240 degree or plus 120 degree. Okay, and for this, the phase voltages are basically the magnitude of the phase voltages are all equal. The magnitude of VAN, magnitude of VBN, magnitude of VCN are all equal, and which is equal to, so this is basically a balanced source. Okay, so the individual phases have to be balanced. So this is known as a balanced source. Okay, so for balance, what it means, the magnitudes should be all equal, but they are shifted in phase. So this is known as the phase voltage, the voltage of A, B, and C with respect to the individual neutrals. Sorry, with respect to the common neutral, the individual phase voltages. So if the magnitude of these phase voltages are the same, this is known as a balanced source. Now, if this VAN, if you do this VAN plus VBN plus VCN, what is the result?
Zero.
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 Is equal to 0. Okay, so but you have to do the phasor addition. You have to do the phasor addition. You try it yourself. Now, what is the meaning of line voltage? There is something called line voltage, which is basically of the form VAB, the voltage potential between VA and B. Okay, or the potential between B and C, or the potential between C and A. And we also what that VAB is. What was VAB?
Root 3 times.
Root 3 times VM and angle 30 degree.
Angle 30 degree.
Minus
At an angle
30 degree.
30.
Yeah. So you have to be very much confident whether it is plus 30 or minus 30, because you have been given a particular phase sequence A, B, and C. So VAB is VA and VBN reversed. Okay, so VB it will lead to a VAB here. So and the magnitude is
Root 3 VM.
root 3 VM. So root 3 VM angle 30 degree. So this is a three-phase Y connection. Okay. So similarly for VBC it is. So this is just the repetition what we did in the just a few slides back. Root 3 VM angle of minus 90 degree. Similarly VCA is root 3 VM angle of plus 150 degree.
Yes, sir.
Okay, so this is just a recapitulation of the earlier. So this is the generator. Okay, because the generator, so a three-phase generator basically consists of three individual single phases. And since this is a balanced generator, by balance what we mean is the magnitudes are all equal. The magnitudes of the individual phases are all equal, but they are phase shifted by 120 degree. Okay, so that is the balanced generator. Similarly, for balanced load, we already defined earlier in the previous slide, the balanced load basically means the impedances are equal. And impedance equal means the real part and the imaginary parts are equal. So this slide, what basically shows is a balanced generator. We have not yet connected the load. Okay, but the points that are to be noted is basically the term phase voltages and line voltages. These are now going to come again and again. Okay, and it has to be crystal clear to you what is the meaning of phase voltages and what is the meaning of line voltages, and obviously it will depend upon the connection. Now in this case it is just the Y connection or the star connection. So in the star connection the line voltage is root 3 times the phase voltage in magnitude. Okay, the magnitude of the line voltage, you see, it basically comes by completing the phasor diagram from the phasor diagram. So in the three-phase Y connection or three-phase Y connected generator, the line voltage is root 3 times the phase voltage, and I am not telling you to memorize it, but you have to realize that it comes from this phasor diagram only. Okay, any doubt from this?
No, sir.
Because we will gradually be entering the numericals on these three phase, and these things will keep on coming, and we'll have to correctly apply the formula.
Sir. Sir, but in question we have given that it is ABC or ACB.
Yeah, that will be given, or that may not be given also. Suppose that is not even given, but this root 3 times this relation holds.
Yes, sir, but we can tell that it is root 3 times, but we cannot tell the phase it is
Yeah,
plus
the
or minus.
phase will change if the phase sequence changes. The phase will change.
Yes, sir.
So if the sequence changes, then only the phase angles of the line voltages change. The magnitude still remains root 3 times only.
Yes. Only the phase angles change.
Yes.
Okay. Now, so this is important below that the line voltage, the magnitude of the line voltage is root 3 times Vm. Okay, so all these things, all of you now should have an individual calculator that I am telling, because all this multiplying by root 3, dividing by root 3 will start now. And you cannot do this orally, or, I don't know if you can do this without calculator. You'll need a calculator extensively now for. So this is the meaning of balanced source. These things should be clear. The balanced source means the magnitudes are the same. Similarly, we studied in the previous slide what is the meaning of balanced load. Okay. Any more question on this? Otherwise, I will go to the next, and gradually we'll do 3-4 numericals.
Yes, sir.
Does we have not determined the line voltages in case of delta connection?
Huh? We will come to that. We will come to the delta connection also.
Okay.
We'll come to delta connection. So suppose you have a balanced three-phase system, where by means what you need a source, a balanced three-phase generator. So a three-phase generator, Y-connected generator, and in electrical engineering language, the one who generates is basically called the source. Okay, because he is sourcing the power. It is sourcing the power, and obviously, since there is a generator, there has to be a load. But before that, as soon as you have a generator, you know where the phasors are, because you have been given the phase sequence. Here explicitly I am not told the phase sequence, I have given the voltages. A is Vm angle 0, B is Vm angle 120, C is Vm angle plus 120. So you know how the phasors are. Okay, so this is how the phasors are. Okay, you can see the phasors?
Yes, sir.
Yeah. So now
Yes,
this is now a generator. So there is what is the now required. So this we just saw that VL, that is the line to line voltage, that is VAB or VBC or VCA. Magnitude wise will be root 3 times the phase voltage. Okay. Now there is also a Y connected sink. Okay, there is a Y connected sink, there is a Y connected load. The load is called sink because the load is absorbing the power. As soon as there is a generator, there has to be a load also. Okay. And then how do you connect it?
ABC respectively.
No, but how do you connect? But through what? What are they called?
So we have to connect.
Y connect.
Suppose your generator is in Bokaro and we are consuming power in Kharagpur. Okay, so this is why it has to be some cables, or it has to be through the overhead transmission lines. Okay.
Yes, sir.
So your generator is at Bokaro and your load is at Kharagpur. Okay, so they have to be connected through some transmission line. We already showed the transmission line. So the A is connected to A, B is connected to the B, and C is connected to the C.
So what does the subscript P stand for here?
Which one?
So the subscript P. ZP.
P is phase.
Okay.
Impedance per phase. Okay, ZP, impedance per phase. Okay, phase, I have given you the phase-wise impedance. Okay, but they all together in the star connected is basically the three-phase load. Okay, now you see another thing. Since this is star connected, the generator is star connected and the load is also star connected. Okay, so there is a fourth terminal coming out of the generator, which the power company may provide to the customer, may not provide to the customer also. Okay, so this is basically the neutral, and so the neutral for the load is given by capital N. The neutral so you see all the subscripts small I have used for the generator, and the capital subscripts I have used for the load. Okay, so these neutrals can also be connected. Okay, So now somebody asked the question. I don't remember, I cannot see the name. Somebody asked the question, how is the circuit completed? So does it answer the question?
Sir, no, sir.
Hmm?
I did not understand. Sir, the
Which one?
current from VA goes to the load A. Then how does it return? Through neutral.
Yeah, I have not yet shown the current. I have just done mechanically connected. Okay. So suppose there was a switch, as if I have not switched on. Okay. I have not.
Sir,
I will show that shortly. Huh?
sir,
Sir, I
sir, what is the meaning of impedance per phase?
Impedance per phase. Per phase means in each phase you have the impedance. You have three phases here.
Oh, acha. Yes.
Earlier I wrote Z1, Z2, Z3. So if all Z1, Z2, Z3 is equal to
Are
ZP.
equal, then yes. And sir, similarly here you have written √3 VPH. That also means that in per phase it is the √3 V magnitude load voltage. A line voltage.
Line
Yes.
voltage. Yeah.
Okay, sir.
Line voltage is VAB, VBC. Huh?
Yes, sir.
Sir, I am actually confused as to how this load is actually implemented. Like, we have various areas in the same region, and each area has a different load, and to each area different phases are supplied, and that as together constitutes the load.
Yes.
Okay, that means this entire thing is not just to one consumer. This is supplied to different consumers, and the loads together is like this. Right?
Yeah, I mean, like suppose if you consider, all of you was watching, say, Eden Gardens. Eden Gardens, whenever there is some match, it will be, lighted up for some games. Okay, so the supply power is a three-phase power. So if this whole Eden Garden Stadium is divided to 3 blocks, okay, one block will be connected through the R phase, one block through the Y phase, and the other block through the B phase. That is how assuming that each block is consuming same amount of electricity. So that is how the power companies will try to balance.
Sir, what is the benefit of connecting the neutral points? What is the benefit of connecting the neutral points?
No, the neutral point is the reference,
To make the circuit complete, sir.
Yes.
Sir, but we can
But
ground it at the both points also, no?
if you have a delta connected generator, okay, then there is no delta and the delta connected load. There is no question of neutral. Okay, so the balance basically takes place to the other three phases because it is all phasor addition. The currents are also going to be added in the phasor form. So we'll shortly show if somebody asks how the circuit is complete. So once we make this circuit, there is now the continuity in the circuit. Earlier it was discontinuous. I had shown the individual generator and the individual source, but now I have connected the source and the sink to a transmission line. Okay, so these are basically the transmission line. Now, what is this figure?
Sir, here also the neutral connection is not necessary. No?
Neutral connection I have connected here. Okay, because the neutral is provided.
But it is necessary, or it will work without that also.
No, we can connect it because we have a star connected load also. Okay, so we have to complete that circuit because there is a star connected load. If there is a delta connected load, we cannot connect.
Sir, I have a question. Sir, if the neutral is always kept at zero potential, right? Like grounded.
It is grounded. In the generating station, it is grounded, actually grounded. Because ultimately, that generating station is the providing the power. There has to be the somewhere the reference zero has to be there.
Okay, sir. Then I have a question. Like, instead of wasting another wire for the neutral connection, why don't we ground it separately at the generator and at the consumer area? Like, if we just ground it at the near the consumer area, then we don't need the requirement of.
Yeah, that is also done. That is also done because that is also done. The return path is to the ground. The return path is to the ground. Yeah.
Yes, sir. That is actually at my place. It is I've seen grounded.
Yeah, it is the return path is to the ground. Yeah.
Sir, but don't we lose that much amount of current in the ground? If we ground it at the point of consuming, then we lose that much amount of current too.
Yeah.
Yes, sir. It is not circulated.
So right now, let us.
So my question was that is it necessary means to connect to the neutral connection? Without that, it will not work.
Without that also it will work, but here since you have a star connected load, there is a point to connect.
Okay, sir.
If it is a delta connected load, you cannot even connect. We will do that type of example also.
Okay, sir.
So this is
Hello,
so
sir.
one.
Sir, the currents vectorially add up to 0 and also the voltages. So in neutral wire, there will be no current anyway. So
we will show it. We will show it mathematically. You will have to actually show. It will all be. It is not. I am not telling just a story. It will be shown mathematically. It will come out. Just we found out now VA plus VB plus VC equal to 0. So we'll also find out what is the neutral current. So let us first allow the current to flow.
But sir, I have like if the consumer, if we send different loads to the consumer, and suppose at one time the consumer switches on one appliance, the next time the other, then the Z will keep on changing. Then it will not always be balanced. So if we want it to be balanced, then this not be a problem?
Yeah, you are correct. It is not always balanced because if suppose you are the power supply company, you don't have any control over the customer. Okay, so the customers keep on changing. You switch on your lights at your will. Okay, and so there is always an unbalance in the system. Okay, but in this curriculum we will not discuss about the unbalanced things. But there is always an unbalance.
Okay.
Still, the power supply companies try to balance it. By shifting the load from one phase to another, all those things they do. But with those things we will not discuss. We will consider an ideal case where the system is balanced. Okay, the load is balanced. But yes, that is correct. If you work in any power supply company, obviously, suppose you are in from Kolkata, the whole Kolkata power supply is controlled from a single control room. Okay, there they can see what are the different phase currents, and there are always these unbalances there. Okay, if you like, all of you will be coming to Kharagpur, and and all of you are in different departments, and eventually sometimes you will be taken for some industrial visits that is basically organized by your department of societies. And if you go to any industry, whether you go to a power plant or a steel plant and all, there you will see these generators present, and there you can actually see the phase currents also. They are getting displayed in the control room, and always there is some unbalance there. But they try to balance it by other mechanisms are there. So those cases we will not discuss in this course. We will consider a balanced system. You see the title, it is a balanced title, balanced three-phase system. Unbalanced cases are basically taught in second year, mostly in third year actually, power systems courses. Okay.
Yes, sir. Got it.
Okay. Now another thing is another assumption: this line wire is having zero impedance. As I told you, your generator may be at Bokaro and you are consuming at Kharagpur. The distance may be say 300 kilometers. I don't know the exact distance, but suppose from Kolkata to Kharagpur, the distance is 150 kilometers. Okay, or say Kulaghat to Kharagpur, the distance is 60-70 kilometers. Okay, now this power that is transported from the power station to the load or to the consumer is through the transmission lines. Now this transmission line, these overhead lines to the transmission towers, I showed the pictures yesterday. They will have any line will have its own impedance. Okay, so it may be 100 kilometer, 200 kilometer. Maybe if the power from Jharkhand is transported to Delhi, it may be more than 1,000 kilometers long transmission line. And you must realize that since it is a piece of wire, it will have its own impedance. Okay, which you cannot neglect. Okay, so in this case, I have assumed that they are having zero impedance. You see, nothing is shown there, but in general, they will also have impedance, and in fact, you may have some numerical where they are also there. Then, but obviously, we will give it balanced so that you can, if it is a star connected load, it will go along with the load impedance. Okay. If I give you the transmission line impedance and star connected load, it will go along with the load impedance, because they are in series. So right now, let us assume that the line wires have zero impedance. And now, as someone was asking, what happens to the current? So suppose the phase current, that is the current from the phase A of the generator to the phase A of the load is called IAA. Okay, current from the phase B of the generator to the phase B of the load is called IBB, and current from the phase C of the load to the phase C of the generator is called ICC. And okay, since we have the neutral current, so let us assume the neutral also having some current INN. Okay, so you see what is happening, that your IAA, that is the current which is connected to the A phase, okay, is what? This IAA is, and here for this A phase, you have one voltage source and you have one impedance. Okay, so due to this impedance, what will happen? IAA will be lagging the A phase voltage. Okay, IAA is basically is equal to VAN by ZP. IAA is equal to VAN by ZP. Okay, and so the angle of IAA, that is the angle, that is the phasor IAA, the angle of the phasor IAA will be decided by the angle of ZP. Okay, and assuming to be an inductive load, because in the system, in the grid, there is mostly inductive load. You have lot of coils. Okay, assuming to be an inductive load, your there will be, it will lag the A phase voltage. Okay, assuming to be some inductive load, so that theta, some arbitrary, it will lag the A phase voltage by a certain angle theta. Similarly, what happens to IBB? IBB is equal to VBN by ZP. Okay, and VBN by ZP, you see this. So VBN by ZP is where? It is VBN is VAN angle 120 by ZP. VBN is VAN angle minus 120. It is just the angle, the VAN shifted by 120. And this is basically equal to IA angle minus 120. So if you rotate the A phase current by 120 degree, you get the B phase current. It is located somewhere here. Okay. Now how to find out the C phase current? So by the same way, it is basically VCN by ZP, and VCN is VAN angle 120 by ZP, and this is equal to IA angle 120 degree.
Sir, here IA we are considering as a phasor only, na?
Obviously.
Yeah, okay.
IA is VAN by ZP, that is a phasor.
Yeah.
It is VAN, and then that ZP decides the net angle.
Yes, sir. I got confused with the angle minus 120 written beside that.
Which one?
No, sir, it's okay. I've understood.
So IBB is IA rotated by minus 120. ICC is IA again rotated by plus 120, further 120, so it becomes plus 120. It is clear?
Yes, sir. Yes.
So now if you apply, you see, if you this star connected load, you see this star connected load, all these currents are going in. So you can apply KCL at the node N. So if you apply KCL at the node N, what will you get? Applying KCL at N, what will you get?
Sir, their sum is 0.
IN, all the
INN equal 0, sir.
IBB plus IC.
All going to 0. So IN is basically equal to minus of IAA plus IBB plus ICC. Find out this value. Well, because what we are doing,
zero, sir.
Yes, sir.
By phasor
It
it will be 0.
So it should be 0. So then for a balanced system, okay, there will be the neutral current is 0.
Yes, sir.
Okay, you can do this addition even by drawing the phasors and see the the resultant of IB and IA and IC is basically 0. So then I neutral current is basically the 0. So this is the balanced three-phase system. Any doubt about
So
this?
this is just because ZP is same for all, and so it is balanced, and hence only the neutral current is 0.
Yes.
Only then.
And this is only there in your curriculum. Okay. But typically there will be unbalanced, and there will be, there may be some neutral current also, but those things we will not do in this course.
Okay, sir.
Okay.
Sir, if I neutral is 0, then what is the significance of connecting it?
It will not be obviously always 0. This is a balance system. For this very special case, it is becoming 0.
Okay, sir.
It means if any excess of current will generate, then it will pass through that wire.
Yeah, if there is an unbalance, then it provides a path for that unbalanced current to pass.
Okay, sir.
Okay, but for this course, we will not consider unbalanced. Okay?
Okay, sir.
So, but you have to be very much careful about these phasors. So, for that reason, you see in every example, every discussion, I am keeping the phasors. But phasors, you should be very much clear what is happening, and then any doubt, as Om had some doubt, all these doubts will be clarified as soon as you go to the phasors. Okay.
Sir, here IA should not be in phase with IAN. Sir, or we assume some impedance there. That's why there is minus theta.
No, this impedance is ZP. The IA only starts flowing whenever we complete the circuit. Only when the circuit is completed.
Sir, there is that's why there is a phase difference between VAN and IAA.
Yes.
Okay, sir.
Assuming there is no other impedance here. Had there been any other impedance, that will also all together along with ZP will decide the lag. Okay?
Yes, sir.
So let us do a few numericals. Lot of numericals are possible on this. So all of you get ready with your calculator. So this phasor diagram is okay. So what we are doing is basically star connected generator to a star connected load. We will see if the load changes also. We'll do the numerical. We'll do that analysis separately. So suppose this is the question given to you, that a balanced three-phase Y-connected load. VL is for a balanced three-phase Y. The VL is given as 300 volts RMS. The load power is 1200 watts at 0.8 power factor lead. Okay, the load is a leading load. Find the line current and per phase load voltages. So you basically have the circuit like this. Okay, I have described with respect to the load. Obviously, there is a supplier. So basically, there is a balanced three-phase load. So balanced means all the three impedances are same: ZP, 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 connected in the form of a Y. And what I am given is the line voltage is 300 volt RMS. So basically, you are given this: the line voltages, line to line voltages. The load power is 1200 watts. That means all the three impedances together consume 1200 watts. Okay. All the three impedances together consume 1200 watts. So what do they individually consume?
400 watts each.
400
Yeah.
watts.
So
400 watts.
So you mind the language, the load power. So basically, in this case, it is, since the load is a three-phase load, it is a three-phase load power. And since we are only doing balanced conditions, so the total
Sir,
power.
I have one doubt.
Sir,
for the entire load, like there are three phases of load, right? So how can we define a single power factor?
That is,
I mean, won't the angles be different with the current and the voltages for each Z?
but phase wise they will be the same, because it is a balanced load.
Individually.
We are considering balanced load. Okay.
I can't understand.
In each phase you have ZP, ZP, ZP.
Yes, sir.
So that ZP will only will decide the lag in that phase.
Okay,
Each,
okay. Acha.
each phase has a phase voltage. See, I have given here line voltage.
Yeah, yeah.
Okay, line to line, say A to C, C to B. But if you consider A to N, that is the phase voltage. And that phase voltage will be how much?
Sir, 100 root 3.
300 by root.
100
by
root 3.
100 by root 3. 1 by root 3 times, because it's the base voltage. Okay.
Yes.
So now do this problem. So the phase voltage, so in each phase the voltage is 300 by root 3. In each phase you know the power. In each phase you know the what? You know the power factor. So in each phase you can find out the what? The current.
So this is power factor given in each phase.
Yes. Each phase there is
Sir,
individually.
VL is, Sir, VL is V line or V load?
V line. Line to line. Whether you consider
Sir,
line or
2.88.
line or load, whatever it is shown. I have given the direction from where to where is VL.
Okay, sir.
2.88 ampere.
So whatever it is.
2.88 ampere.
So this is the phase voltage. Okay. So if this is the phase voltage, then
Sir, in each of them it would be root 3 by 4, and the angles would be minus 37, minus 157, and 83 for the currents in the different wires A, B, and C.
yeah, but you find out what is required in line current, and you have asked to find out the per phase load impedance.
Oh, load impedance. Per phase load impedance.
So phase voltage is, which is Vp. So this is basically equal to VL by root 3.
100 root 3.
VL by root 3, because this is a star connected load. Okay. And this is equal to what?
100 root 3.
300 by root 3. Volts
100.
RMS.
Yes.
So all those things we can do. Maybe we may not do it because we may need get some other advantage if we do all those calculations at the end. So this is the phase voltage. Then now this current is going in, which is basically the line current. This is the line voltage, line current. So what is happening here? The line current, what is the relation between the line current and phase current here?
Line current is equal to root 3 times phase current.
Line current equal to root 3 times phase current. Line current is directly line current is directly going and entering the phase. Line current
root
is
3 by 5 angle minus 37.
Line current is directly entering the phase.
Both are equal.
Yes, sir.
ZP by ZP.
So line
Both
current
are
is
same. Both are same.
both are same.
They are equal, sir.
This is a star connected load. You have to see, you can physically see. The line current and phase current are same, because the line current is directly entering the phases.
Yes, sir.
Okay. So phase current is equal to line current. Now, if you draw the phasors, your phase is here, phase voltage. And your phase current is somewhere here, because it is told that it is leading. Okay?
Yes, sir.
Okay, it is told that it is a leading load. So if your phase voltage is Vp and your phase current is Ip, then this will be the phasor. Okay. So now find out what is the line current.
So 16 root 3 by 5.
So you see here your theta minus phi, according to the convention that we have studied so far, our we introduced the angle theta with the voltage and phi with the current, and theta minus phi was the angle between Vp and Ip, according to the convention we studied earlier. And in this case, what will happen? The theta minus phi is basically less than 0. Theta minus phi is basically less than 0. Okay, in the way we have introduced the subject, theta is the voltage phasor, phi is the current phasor. The voltage phasor we assume to be ahead of the current, and then theta minus phi was positive. But here, the current phasor is ahead, so theta minus phi is basically negative. Okay, so what type of load it is?
Capacitive.
So that you have to keep in mind when you because you have been asked to find per phase load impedance.
So can I ask one question? Sir, in this diagram, the way we have defined Vp, Ip can be Vp by Zp, right? Like
Ip will be Vp by Zp.
So like Vp is phase voltage, right? So how can then Ip also be equal to IL, since IL is VL by Zp?
No, IL is not VL by Zp.
Achha, we are not defining it like that. Okay.
No. I am not telling you. You just see from the circuit. I am not telling anything. You know the voltage relation between voltage, current, and impedance. Okay, but see whether is VL across Zp.
No.
No, the phase voltage would be. That would be.
So the phase voltage is across Zp. Okay, so yes. You have to follow the circuit. I am not telling anything from memory or something like that.
So, but like then how do we generally define line current?
Line current is the current that is coming from the line through the transmission line.
Okay.
These are the line current. These are the line currents. But if it is a star connected load, the line current is directly entering the phase.
Okay, understood.
Okay.
The answer is 28.9 and it is leading 36.87 degree.
28.99, what is this?
28.9 ampere.
2.88.
28.9 ampere.
5.54.
Sir, 2.88, yes.
2.89.
So the load power is given is 1200 watts. What is the per phase power?
400 watt. 400 watt.
Okay, so in each phase, 1/3 of the power is getting consumed. So because we have, and obviously, another thing is important. Load power is 1200 watt. I have given, you see the unit is watt. I have only given you P. Okay. I have only given you P. In AC there is another Q also. But I have only because we are only concerned about the real power or active power, and that is given to you.
Active power. Okay, sir.
Okay. So what is the equation? Per phase wise, power is equal to VL/IL VI cos phi.
Cos theta minus phi.
So this is 300 by root 3. This is the voltage across each phase. I am doing the calculation per phase, power calculation. So it is 400 equal to 300 by root 3. Okay. IL is not known. IL which is equal to IP, that is not known. Into 0.8, the cos phi. Okay, so from here you can find out IL equal to how much?
8.6.
2.8.
2.88.
8.66. How do I don't know how to,
2.89
2.88 and yes,
2.89, yes.
ampere. Okay.
36.87.
So this is the load current. And since this is a star connected load, this is the same as the phase current. This is the magnitude of the load current. So from here, you know Vp, the per phase voltage. You also know the phase wise current. What you can find out? The phase wise. So you one part of the question is answered. You are asked line current. You have got the line current. Okay, so you can find out the impedance.
Yes.
The absolute value of the impedance, which is equal to the voltage by current.
60, yes.
300 by root 3.
It will give 60 ohms, sir.
Yes, sir.
Something it will come. So 60 ohms. Okay, so you have got ZP. And that is the absolute value of the impedance you got. Then can you find out the components?
Yes, sir. I square R is equal to power for R, and then
Why do you need to go to power?
Power factor.
V is IZ. Z.
R by Z is power factor. Okay.
Yes,
so
sir.
Z,
Oh, yes,
so,
sir.
so ZP is equal to.
Yes.
So ZP.
48 or 12.
So you see your ZP is equal to 60. That absolute minus of cos inverse of 0.8.
Yes, sir.
Whether it will be minus or plus.
Minus.
Because it is a capacitive load.
Yes, sir.
Yes, sir.
It will be R minus Jx form. Okay. It will be R minus Jx forms. For that reason, you see, you have to mind the type of power factor, whether it is leading or lagging. Okay. So then through your calculator you can find out cos.
So can we write power equals to V square by R? Is that correct method?
No.
Power equal to? But where is your R here? You don't know R. Are you given R?
No.
Say we can use Z.
And also
Yes,
is not
sir.
considering power factor.
You are not considering power factor also.
Sir, how did we know that this is capacitive circuit?
You read the question. What is the power
So the
factor?
current is leading, that's why.
I have highlighted leading power factor.
Current is leading,
the
that
power
is
factor.
capacitive.
Okay.
Yes, sir.
48 minus 12.
Yeah, so you can find out all those cos inverse, cos theta, sin theta, you can find out. So it will be ultimately R minus Jx. Okay, you can find out cos 36 degrees, sin 36 degree, and then multiplying by 60, you can represent it in the form R minus Jx. Since this is minus, it will lead to sin as minus. Okay. Sin theta will be negative.
Sir, IL is RMS current, no? So exact IP means we need to multiply it by √2 to get exact magnitude. Means it is.
Everything is here is in RMS. I have given you the voltage in RMS, means then whatever phase current, load current, line current, everything you are getting in RMS.
Okay. Okay, sir.
Okay. So let us do another numerical.
Yes.
Okay. Let us do another numerical.
Sir, actually I had doubt that in the per phase power, sir. So that we have written 300 by √3. So actually the load power per phase is, sir, 400. So we will
No,
take
I have not written 300 by √3 per phase power.
No, sir. So I'm telling that, sir, if 400 is the so voltage along, sir, so the power along, sir, one phase, then why we will take the voltage and current in only that phase, sir.
So that is only we are taking, ne?
So but 300 by √3 is along the, sir.
Is Vp, is the phase voltage.
Yes, sir. So it is, we have to take, I think, VL, sir, there.
Why?
So
Just
actually
along one phase. Why? We are only considering what is happening between A and N.
VL is applied across AC, not AN.
So we are only interested in what is happening across AN only, because we are handling per phase.
Okay, sir. Got it, sir.
Okay.
Yes, sir.
So we will do. You do another numerical. So there is a Y-connected load. Each phase has 3 loads in parallel. Your AB, that is the line voltage, VAB line is 400 volts RMS. You are asked to find out the phase voltages, phase currents, total power drawn by the load. So suppose this is your system. So VAB is 400 volts RMS. So it is a Y-connected load. Each phase has 3 loads in parallel. So basically I have drawn another diagram because each of your ZP basically looks like this. Each ZP is actually like this. There is minus J 100 ohm, but that means it is a capacitor, minus J. Then there is a 100 ohm, which is a pure resistor. And then you have a resistor and inductor in series, which is in parallel with the earlier two. So that is individually your ZP. So you are given the line voltage VAB, and you are given the impedance across in each phase, per phase impedance, which is in this form. So find the phase voltage, the phase current, and the total power drawn by the load. So what will you do first?
ZP is equal to 50.
Z equivalent.
Sir, first we find ZP.
So find out the Z equivalent.
Yes, sir.
50.
Huh?
50.
Pure resistance.
Sir, 4.62 is phase current.
4.62.
Is phase current, sir. 8/√3.
So ZP is coming to be 100, sir.
Huh? So you see that they are in parallel. So if you combine them, so it is 1 by ZP equal to?
So Z equivalent equals to 50 ohm.
100, sir.
50
Z
ohm,
equivalent
exactly
50.
100.
Z equivalent 50. 50, sir.
50, sir. 50 it is coming.
So this is 1 by ZP is equal to 0.02. So ZP becomes
50 ohm.
50 ohms. So now find out. So if your VAB is given 400 volts, suppose your VAB is 400 volts. Since your VAB is, what is the phase voltage? What is the phase voltage?
400/√3.
400/√3.
√3. So the phase voltage and line voltage, will they be in phase or there will be a phase difference?
They will be in phase. In phase.
In phase.
Because
In phase.
sir.
In phase.
Phase difference.
No, sir, phase
They
difference.
Huh?
But we don't know.
You don't know.
So they will be in phase.
Resistive circuit is present.
Yes, sir. In phase.
because the resistance has no part.
Purely
Phase
resistive
difference.
No. VAB is coming from some generator. VAB is
It's
connected.
out of
from-
phase 1. Yes, sir. Out of phase.
So how will it be? Suppose VAB is angle 0, at an angle 0. Where will VAN?
Sir.
So 1
I have kept the VAB along the reference.
VAN will be minus
Minus 30.
Huh?
Minus 30.
Minus 30
minus
degree.
30.
Minus 30.
Minus
You
30,
you go
minus
back to my earlier thing. So
Plus
Minus
30
30
degree.
VAN will be minus 30, sir.
Minus
VN
30, yes, sir.
Yes, sir, minus 30 degree.
Yes, sir.
30, yes.
Okay. Okay. So where is VAN? Minus 30. So where is the phasor?
Minus 30 degree
So at
from
a,
Minus 30
clockwise,
degree in
like
the
below the
fourth
reference.
quadrant.
Below the reference. You go and
Yes.
see my earlier thing. So here I have aligned the VAB, the line voltage along the reference. So then you have to
Yes, sir.
give the phase voltage appropriately. Okay. Now where will be the phase current?
So along VAN.
Along VAN, sir.
IA is equal to?
Along VAN.
Because it is purely
VAN by
resistive divided by 50.
Yes, sir. 8
Okay.
by root 3
Yes,
angle.
sir.
So you will get some value.
8 by root
4.6.
4.62. Just check whether my value is correct or you rectify me. I will correct my notes.
Yes,
No,
sir,
sir,
it is
correct.
correct. I also
Correct.
got same.
Yeah, so this will be aligned along with the voltage phasor.
VAN.
Yes,
VAN. So you are asked that VAN and IN both you have found out. So now found the total power. You can
3,200 watt.
Huh?
3,200 watt.
So you can find out phase wise. Okay. So what is the power
Phase
expression?
wise.
So per
Sir,
phase power is
VRMS
how
into IRMS. VRMS into IRMS. 3,200 by 3, sir.
So per phase
power is
power.
3200.
So it is what?
3200 by
VL, it is the, what is the power expression? We are doing AC. VL, IL cos theta minus phi.
Yes,
Because
sir.
we are doing per phase. So this is VL. In each phase, this is the voltage. Okay. And what is the current? Current is this. Okay. This is IA. Now what is theta minus phi?
0.
One.
Per phase it is 0.
So cos 0
Cos
degree.
0.
So 0.
Zero.
Okay. So the total power equal to 3 times this. If you multiply by 3, this denominator goes. This 3 root 3 root 3 goes, and cos 0 is in 1. So it is 16 into the power 4 by
3200.
3200 by 3.
50.
So 1066.67. What?
Huh?
320 by 3.
1066.
3200 total power input.
Okay.
Yes, the total power will be 3200. I was talking about only one power.
Okay.
Yes, sir.
Yeah. So now do another sum. So you have to be very clear how the things are being worked out, per phase basis, and how the angles are changing. You have to be alert, if required, keep on drawing the phasor diagram. Otherwise, you'll make a mistake. If you just apply the DC formula and all, okay, for this it may be correct because it is purely resistor. But as soon as there is some angle, the answer will be wrong. Okay. So let us do another numerical. A little bit complex. I will give you 2 loads now. Okay, is it over?
Yes, sir. Yes, sir.
Yeah.
Yes, sir.
So there is a three-phase, three-wire system where the line voltage is 500 volts. Obviously, I have given it in RMS. Now there are two balanced Y-connected loads. There are two balanced Y-connected loads. Find the phase voltages, line currents, total power drawn by the loads, power factor at which the source is operating.
Hello, sir.
Ah.
Sir, in the question, how we consider it is given in RMS or in the peak value? Because in question it is not written.
It is not written. You know, this confusion arises. You know, if nothing is written, it may be the mistake of the question setter. Also, it may be. You know, so by you can make some assumption and carry forward. You know, but most of the times you should consider it as an RMS. Okay. So you are basically given
Okay,
this.
sir.
You are basically given two loads, two star connected loads, two Y connected loads, two balanced Y connected loads. Each of them are balanced. So the first load I have given the name A1, B1, C1. The second load is given the name A2, B2, C2. So for the first load, the per phase impedance is Z1, which is equal to 7 minus J2 ohms. For the second load, the per phase impedance is Z2, which is 4 plus J2 ohms. You are given the line to line voltages 500 volts RMS. VAB is given. So
Excuse
you
me,
see,
sir. Sir, can we say that the neutral points are connected, or do we have to not take them as connected? Means N1 and N2 we have to assume to be connected because both of them are like ground only.
no, here they are not connected. Like suppose you have a load and your neighbor also has a load. Do you connect with your neighbor?
No, sir. But actually, if they are ground, then it will be like
No,
connected.
right now it is not connected. Okay.
Okay. Okay,
All
sir.
the return path is to the phases. You have a motor, as I am
Sir.
telling you, and your neighbor also has a motor. Will you connect with each other?
No, sir.
Sir, in the slides you have mentioned that three phase three wire was delta connection and three phase four wire was star.
No,
So,
three phase four wire is star, but you may not even use the fourth wire. Star is such a thing that the fourth wire is available, but you may not connect the fourth wire. The fourth wire may not be made available to the user.
Oh, the neutral point is not having a wire there. Achha.
Okay. Okay, now you see each of these loads, I have given you two loads. Both of them are star connected. So they will, in each of these loads, there will be a phase current. Okay, so what is given is to you is VL of 500 volts, the line to line voltage, which you can, so if we assume that VAB is 500 angle 0, you can draw the reference phasor. So if that is your reference phasor, so what is the, phase voltage?
500 by root 3 minus 30 degree.
Yes,
sir. So this is your VAB, which is 500 volts. So VBC, VCA, all you can draw. Okay. VA, VBC, all the line voltages you can draw. If anything is required to be found out, you can. It can be easily constructed because you have aligned VAB along with the reference. Okay.
Sir, is IL 97.53 angle minus 10.61 degree?
What is your name?
Karan Kumar.
अरे Karan, you are super fast, huh? कहाँ से हो?
I'm from Bihar.
Oh, so you are इतना जल्दी कैसे कर लेते हो? इसलिए फेजर वेजर सब है?
Sir, calculator.
Anyway, calculator is giving everything. Yeah. So anyway,
Yes,
so
sir.
you have to understand the steps. VAB I have kept at 0, so VBC is 120 degree, VCA is 120 degree plus. So VAN, that is the phase voltage. because here star connected load. Okay, so the phase voltage is.
So what did you say? The answer was 97.511 angle minus 10.63 degree. This one.
6
For the IL.
No.
Oh.
Magnitude is okay. Angle is wrong. है ना? So this is VAN is at an angle minus 30 degree and the magnitude is 500 by root 3. So basically your VAN is somewhere here. Now once we apply this, what will happen? There will be individual currents going to the loads. There will be individual currents going to the loads, I1 and I2. And these I1 and I2 added will become IA. Okay, you are asked to find out the total line current. Since there are two loads, both the loads will contribute to the line current. So you have to basically find out both the currents, phase currents individually. Okay. So your I1 is how much? VAN by Z1. I have given you Z1. So what is I1? What is the value of I1? Somebody should tell. You are given voltage by impedance. So you have to find out the magnitude of the impedance and the angle. Divide one magnitude by the other and the magnitude of the impedance will be subtracted from this angle.
Sir, 39.65 angle minus 14.0.
Okay, so it is 39.65 angle minus 14.0.
Angle plus sir 15.94.
Angle plus होगा?
No sir, angle minus.
Negative है.
No sir, angle minus होगा.
Minus आएगा sir.
Okay sir, sorry sir.
Okay, so as soon as you get I1, you can also show it in the phasor. It is at an angle 14 degree and it is somewhere here. Find out I2.
$64.54 angle minus 56.56.
Okay. Where is it located?
Yes, sir.
Yes, sir. The 64 degree and angle.
And where it is located, what you can draw? Minus 56 degree. Somewhere here it is located. Magnitude wise larger than I1. Okay. And then you get IA, which is equal to I1 plus I2. That the total line current is equal to, since there are only two loads, both these loads added together, phasor addition, will give you the line current. So which is this? Is it this or something else?
Yes, sir.
Yes, sir. This only.
Okay, so phasor wise it is. So it will be somewhere in between I1 and I2. So because the angle is minus 40 degree, and with a magnitude of 97, bigger than I1, I2. You know, I could not hold it in the slide, but it will be much larger if you draw it to scale. So that is the total line current. So total power drawn by the loads. What is the expression of power?
Sir, VI power factor.
VI and the cos of the angle and the cos of the angle.
Angle between
voltage and current.
So one question is the power factor. So power factor is the cos of the angle between the voltage and the current per phase. So VAN, what is the angle?
Sir, we can not do I1 square into 7. So directly can't we do I1 square into 7?
I1 square.
Yes, sir. Same answer.
I1
I
square.
square R.
Huh?
Sir, I square R, by using I square R without power factor also here we can do.
Yes, sir.
So
Means
that you can
I1
do.
square. Sir? So using I1 square into 7 plus I2 square into 4 into 3 times.
3 times.
You can do, but in your question, if you are asked to show the phasor diagram, may have half of the marks.
Okay.
So power factor is the angle between VAN, IN and the cos. So VAN, the angle is minus 30. IA is at an angle minus 40. So in between the angle is 10 degree.
10.7
It is basically cos of minus 30 minus of minus 40 degree. Which is equal to?
So 10.7.
0.9826.
10.7.
Yes, sir. Got it.
Because the current is lagging the voltage, so it is lag. Current is lagging the voltage by 10 degree. So it is overall lag, 0.98.
Yes, sir.
0.98 is correct or wrong?
Sir, got it. 0.9826.
Yeah, so now the phase power, total power.
Correct, sir.
The total power supplied by the source or the supplier is 3 times the per phase power.
2.94.
So 3 times what? Per phase voltage is how much? 500 by root 3. This is the per phase voltage. Okay. And per phase current? 7.5.
97. Yes.
Multiplied by?
97.5.
Multiplied by 0.98.
Yes, sir.
Yes, sir.
The power factor. So you see 3P, 3 VL, 3 VP, IP cos phi. What we have done? We are calculating the power per phase. So we are doing 3 VP, IP cos phi. And then you can do this by a calculator. And that the answer is
82.75.
82 point?
Kilowatt. 75.
82.7 kilovolt.
82.98. 82.9. Yes, sir.
75 or 97? My answer is wrong or also?
I got 7.4.
I also got 7.4.
7.4.
7.4, sir.
7.4, sir.
Anyway, so this is the total power, So what we have learned today is, star connected generator connected to star connected loads. We have done single load, we have done multiple loads also. Hello. मैं थोड़ा क्लास में 2 मिनट बात कर So this is the star connected load we have done. Okay. So we have, in the earlier problem there was a single load, now we have got 2 loads. And we have seen how to calculate the voltages, currents, find out the per phase currents, and then to find out the line current, and then the power factor and the total power consumed by the load. So here in this case, this is 3 phase. Total power means what is the sum of the total power by the individual phases.
Excuse
so
me, sir.
finding,
So if you take the power factor as 0.9826, then we will get the same value of total power, which
As
is
me.
92.97.
Yeah, so that I must have done, because
Yes, sir.
Maybe the previous value of power factor, whatever is there in my calculator, I use that to do this computation.
Yes, sir. Yes, exactly.
Yeah. So, so you have to practice this type of numericals. So we will stop today. Next day we will do, if the load is of delta connection.
Okay,
the load
sir.
is of delta connection, and also, but everywhere it will be the similar approach, and we have to keep on doing the phasor addition and handling these complex numbers very carefully. Okay.
Sir, I have one
Thank
thing
you,
to
sir.
ask. Sir, I mean, not related to this problem. You previously said that in